Okay, I think we can start because it's already 1 o'clock, 4 o'clock. Well, hello everyone. Welcome to the TMSi Expert Talks. My name is Leonie Terstegen and I will be your host for today. Today's webinar will be a bit different than normal because we have our own junior research engineer as our speaker, Joost Herijgers, and he will tell us all about our new developed TMSi Python interface. He will walk us through, he will show some examples, and he will, of course, answer all your questions. Of course, if you have any questions during the presentation or during the webinar, you can use the Q&A button on the center bottom of your screen. What you can also do is save your question for after the presentation, and then I can unmute your microphone and you will be able to ask your question to Joost. There's a lot to tell and a lot to show, and I'm really excited and I hope you are too. So I would like to invite Joost to take over and show us all the new functionalities for the Saga.
Thanks for the brief introduction, Leonie. So welcome everyone to this webinar on the TMSi Python interface. My name is Joost Herijgers, and as Leonie already told you, I'm a junior research engineer at TMSi. I've started in September 2020, and actually the main project I've been working on will be shown in this webinar, as the TMSi Python interface has been a really intensive project with our team to get it up and running for you. And today I'll give you some short introduction and advice on how to work with the interface. So what are we going to do? We're going to work first through a brief introduction, then I'm going to show an overview of our library. After that, I'll give you a short demo where I'll illustrate some of the examples that you can also find in the TMSi Python interface. And after that, I will give you some best practices, so some advice on how to develop your own code with the library that we developed and things that we encountered ourselves that are really convenient to know about before you're going to write your own code. And then at the end, and I hope that will be the majority of this webinar, there will be the Q&A session as Leonie expected. So I'm happy to receive your questions and give an answer to that. So to introduce the TMSi Python interface, and specifically the Python programming language, I can imagine that many of you already have heard of this programming language, as it's an increasingly popular programming language. If I have a look at myself, during my master's education, I started encountering Python more frequently and more frequently, whilst in all phases before that, MATLAB was the main dominant programming language with which we worked. So you can also see that there's a real increase in interest in working with Python. And it's not that strange because Python offers a lot of free to use and well-developed libraries with which you can start doing a lot of nice stuff relatively easily. So our TMSi Python interface is also such a library that's available for free to you. And with the TMSi Python interface, you can interface our Saga device to the Python language. And with that, you get the possibility to really integrate your Saga in an online processing environment with tools that are available to the Python language, which make it quite nice for your setups so that you can get multiple type of experiments up and running in your labs. What we did is to give some different examples, and the different examples are mainly there to highlight the different syntaxes that you need and to highlight how to develop your own code for work in the lab. It's good to know that we distribute it under the Apache v2 license, and this means that it's free of charge for you, but if you're gonna redistribute code, it's important that you keep mentioning the official license and notice files that we have also delivered with this. So the currently supported functionalities, of course, this is a list that will be extended in future releases as well, but for now we started with a basic interface. First of all, you can adapt the device configuration. You can do so in two ways, either by changing your device configuration in one function call, more on that later, or you can, as would be more known to you probably from past experiences, to do this property by property, meaning that you can first, for instance, change the base sample rate. Next, you would choose to configure triggers to enable those. So that's also still an option. Another functionality that we support is to sample data from our Saga system, and that you can save this sample data to the Polybench native Poly5 files. What you can also do is to load these Poly5 files that you recorded. It's not only files that are recorded in Python, but also files recorded in Polybench. So whether you are wanting to create really the online processing with your Python interface, it's convenient anyway to download it, as you can now directly read in the measurement files from either Polybench or the Saga interface from MATLAB or the TMSi Python interface into your Python processing environment. One last functionality on which we had worked in this release is to plot the sample data so that you can immediately see this. And that's both implemented for sample data and impedance data. And for sample data, we also decided to create an example class that allows for some online processing on the data. In this case, one very convenient and logical step we thought to do this first is to apply a filtering class so they can filter incoming data, which is only there for display, not for saving the data, but just to plot it together with a filter. So that brings me to the overview of our library. I'm not sure if any of you have already downloaded it, but if you have downloaded it, you will see in our main folder, you will see an examples folder and a TMSi SDK folder. The TMSi SDK folder is the main library, and in this folder you'll find several framework classes, such as device or error or file writer. And these different framework classes actually make up the architecture of our library, meaning that, for instance, if we take the file writer as an example, we have a base outline there to which we could kind of involve or add different types of file formats to that, so that you would use only a single type of syntax to get the file writer up and running, which makes it a really easily extendable framework. The same goes for the device, of course. Currently, we only support the Saga device, but we will also ensure that all future devices that we will develop will also be supported by this Python interface. And what we have done right now in terms of file formats, as I already indicated, we have decided to create a Poly5 file writer, and we are already working on our first other file format, which is the extensible data format. Maybe some of you have encountered this when using Lab Streaming Layer, but we are looking into that, how to implement this. Of course, if you have any suggestions, we are happy to receive them, because that will definitely help us to improve the support that we can give you, especially in terms of writing to different file formats in this case. We have a file reader, as indicated, just for the Poly5 files at this moment. We have the filtering class as an example to how to do your online processing. And we have some plotters, both for impedance data and sample data. So now that we all know what's in our library, it's important to get a hang of how to design an experiment, how to write your code in a way that you can sample data from Saga. So in Python, it's important to first import relevant libraries. This is just an example. It's not the full import for the upcoming workflow, just to reduce some space on my slides. But what you can do is either import a library as a whole. In this case, you would import TMSi SDK, or you can import sub-elements from the TMSi SDK. So in this case, we would directly import the TMSi device class, which was also in our framework just presented. So that's step one. Step two is to initialize our SDK. And you do this by calling TMSi device and then call its function initialize. This is always the first step that you need to do, as this will initialize the DLL functions associated with the device. The next step is to create a device object, a handle to a device object. What you do is that you both specify the type of device. Of course, currently this is only the Saga device. But what you also need to do in this step is to add the interface type over which you want to connect. And in this case, I've chosen to display the kind of regular USB docked, which is just a stationary setup for Saga. After creating the handle to the device, we can open the connection, calling the open function of the device class. And what we can do then is to start changing the configuration. And what's convenient, as already said, they can upload a configuration in one go into the device. In this case, you would do that using the load config function of the device class, and specify the absolute or relative path towards your configuration file, which is stored in an XML format. More on that later, but this would be the syntax. After changing the configuration, you need to, if you want to save the data, that is, configure your file writer. The file writer can be configured using the following syntax. In this case, you would initialize the file writer class, and again, you specify the type of file format. We expect that we can thus earlier in a next release extend the available file formats. For now, only the poly5 file is available. And what you can do, we also need to configure in the file writer is to specify the path and file name to which you want to save the data. In this case, I've chosen for a path relative to the path from which I'm running the example, and I've chosen to name my file example measurement. We have ensured that a timestamp is always added to your file so that you won't overwrite any existing files, as that would be an inconvenience. After creating the object itself, you need to open this, and you need to open it by also passing the device handle, as then the coupling is made between the two objects. The next step is to retrieve sample data, and you can do so in two ways, which is why I've also highlighted that in italics. You can either do that via using a plotter object in which your data is going to be shown on screen. To do so, you need to configure some Qt widgets from the PySci2 library, and you need to initialize a real-time plot. And in that, you can specify a name, you need to specify the device handle again, and can insert a channel selection that contains the channels which are displayed from the start of your measurement. After that, you show the plotter window and you start the event loop, and the event loop keeps running and running until your measurement is stopped, and you stop the measurement by closing the plotter. What you can also do is to outright start a measurement without a plotter. In that case, you won't be able to see your data, but your device will still sample data. What you do is that you call the start measurement function of the device. You insert a sleep so that nothing will be executed in your main script. However, all the different threads that run in the background will be able to continue. So you will be able to continue reading data from your Saga and also writing them to disk. After the sleep is over, you have to call the stop measurement file to stop the measurement. And basically the plotter also contains a start measurement and a stop measurement function, but then it will start once you start the event loop, and it will stop once you say, or once you click away the plotter window. The final step in your workflow would be to close the file writer and the connection to the device, and it can quite logically and straightforward do that using a close function with handles to both objects. So that brings me to the examples part, and here I'll show you a short demonstration in a bit. There are 11 different examples, as you might have seen, and I'll first show how to adapt the configuration using either the XML call or using a property. Then I'll show an example of online plotting, where I'll show some data from an accelerometer and bipolar EMG. And after that, I'll also show those same signals, but then with the filtering object applied to it. So I have to switch my screen for a bit. And I hope they can all see my spider environment right now. I will zoom in a bit for you. In here we see the code of one of the examples that can be found in the library. And I'll start by changing the sample rate. My Saga is already coded on, so I can run the script. What you then see is that the DLL is loaded. We create a handle to it. That's the device initialize. Then we retrieve the current sample rate. We update the base rate from the standard 4000 Hertz to 4096 Hertz. And then we update the groups, which is highlighted by me right now. You can call it directly by all types. You can use individual channel groups, and you can see in the output that's printed that we updated the sample rates per group. The other possibility makes use of the load config functionality, as you can see here. If we do this, we will try and load first a minimal configuration containing one auxiliary output and one unipolar input. Then we will update the channel list to all channels to be enabled, unipolar channels to be enabled, and write it and save that again to the Saga current configuration XML file. That's something else you can do, of course. Then I'll show you a short plotter example. And in this plotter example, multiple things are going on. First of all, we need to ensure that the right channels are enabled. So we will enable all outputs from the first auxiliary channel. So Python starts counting from 0, so we enable number 0, 1, and 2, and we'll enable the first bipolar channel. And that's can be seen over here. After that, we will connect the file writer and start doing the measurement. So I'll quickly connect all the cables so that we can see this. And that's that. So let's start this measurement as well. We again load the DLL function, as you can see, and now we will see the plotter popping up in a bit. May take some time. You can see that the Poly 5 writer started, the devices started sampling as the producer started indicates, and then we can open the window. So all channels will start in an unscaled version, except for the status channel. So I'm pressing the marker button now, and that has a base value. So we can press auto scale so that we get some activity there. And you can see that I'm now contracting my forearm muscle in the first channel. What I can also show is this accelerometer. Right, it was just lying still on the table, so it's therefore quite hard to see the changes. And if we move this around, you can see that the value starts to change. The plotter nicely indicates this. and it will put it on the table again. We can increase the time ranges. We can say, okay, we want to hide all auxiliary channels so that we only have the status and bipolar channel left. We can also enable them all in one go. We'll come back unscaled again. And that's basically how you would use the plotter. So I'm closing this right now, as said, and we stop sampling. The file writer will close and we will have a new measurement file over here, which is example with an aux measurement. Okay, then let's move on to the filtering. I will apply a high pass filter. That's the only thing that will be done in this case. I can also choose for a band pass filter. I think that for combining an accelerometer data and a EMG channel, that it's most relevant just to show the high pass filtering. Let's wait again for a little bit. The plotter is coming up, and again need to scale the data. Now we can see again, still we have some scaled data here. You can all see that the offset is now removed, and we have very small voltages and also the accelerations close to 0G. What we did in this case is that we added a filter object just after defining the file writer and before defining the plotter object. Same goes again, we can close the plot and we'll stop sampling from the device. And with that, we have shown you some examples. I will switch back again to my presentation because I still promised you to give you some advice on best practices. So let's continue with that. So it has been a repeating subject already in this webinar, but it's very convenient to store your configuration in the XML files, especially if you're working together with some colleagues on different experiments. It's easy that you would have your own configuration stored, can directly load it into the device, and you don't have to do any adaptations anymore. So that makes it quite user-friendly to have the a quick setup for your measurements. An XML file, I'm not sure if many of you are familiar with it, but it would look something like this. In this case, this is an example from a device. You can see that many of the device configuration properties, such as the base sample rate, is stored, but also the alternative channel names. In this case, it's a example that has a 500 Hertz EEG setup. As you can see, that the device is stored there with a value of 3. What you can also directly do is to specify the full path to your folder where you save all the data when you initialize the file writer. This makes it very clean to find your data again after completing your measurements. One thing that I want to stress and already highlighted a little bit during the demo is that changing the channel list may be a little inconvenient. So therefore, some additional explanation to go with that. It consists of 4 steps. First of all, you want to configure a list with all the channel numbers associated with the channel type that you have, which should be enabled in your calls. Next, you want to retrieve the current channel list from the device. This contains which channels are active, which are not active. And then you will start a loop over all channels. And in that loop, you will have to build some statement which controls if the channel is within your pre-configured list or not. If it's in the list, you want to enable this and you want to disable all others. At that point, you will have a updated list, but you haven't pushed this to the device yet. So it's important that you update the channel list by sending it again to the device. And you can do that actually with the same call as with the original retrieval of the list. Then something else, mainly on the development environment that you'll be using. If I speak for myself, I really like the Spider IDE. as I started using it coming from a MATLAB environment. It's quite similar to it. You also just saw it in the demo, and it has quite some nice things to show your data and also review some of the variables that are there. It is, however, important to pre-configure your preferences so that the graphics are plotted in line. This is a setting that can be found within the Preferences tab below Tools, and there you have to change the graphics to be plotted in line. Otherwise, the library will fail due to a compatibility issue between two libraries between which we had to choose. Another best practice, mainly when you are starting to write your own processing code, is when you would start doing so, it's good advice to start a look on how we implemented the real-time filter class, as this contains some basic layout on how to initialize this, how to do some of the preparation steps that may be different from the initialization, such as in our case, configuring the cutoff frequency for the filter. And it also will contain a sampling thread, which will do most of the processing. Each processing thread that will consume data from the device needs to be registered to the sample data server, one of the framework classes which we have developed. And you have to register each thread using the device ID and a queue object. And a queue object is a built-in Python object that can be relatively conveniently used. So what you do is that you specify the queue size, which determines how many elements may be in the queue. Then you specify the queue itself and make sure they can access it in the class. Then you register your processing thread using the device ID and the previously created queue. And then you will start a measurement. And then you can, in your processing thread, retrieve sample data from the queue sample sets queue using the get function. It's very important to move the heavy processing to different threads and also use different queues for that. That's also why we developed the sample data server. And for instance, the plotter and file writer will also each have their own queue from which they pull the data from the device so that they can work independently of each other and there's no risk of using the wrong data or skipping, for instance, a set. One final remark on that is when you start using GUIs, it's important that the updates to your GUI, so in this case, for instance, for the plotter, to be done in the main thread, otherwise you won't see these changes coming up. You can, of course, prepare all the data to be plotted and to actions that follow from a button click, for instance, to be done without outside of your main thread. But it is important that the exact update is in there. So then I want to end this webinar again with a short demo. For that, I need a colleague of mine where we'll demonstrate how fast we can start measuring our EEG. So I'll be switching again to my Spider environment. And with that, I can also ask Param to come and sit a bit closer. Yeah, you can move a bit like this. It's okay. So what we're going to do is that we'll show how quick we can measure. And doing so, we will do using a water cap. And right now we have prepared the water cap with all sponges. And we'll hang this in a bucket of salt water, as you can see over there. Can go in for a bit, a second or 5, something like that. And then after that, we will connect it. We'll be there for a little while. I'll already start running the script, which is also one of the examples that come with the interface. It will load in the previously shown EEG configuration, and then it will start an impedance measurement, after which we will start a sampling measurement. So let's run the script. Aram is preparing a bit to put on the cap. And I think you also need the patient ground. So right now we have the head view of the impedance plot. As you can see right now, there's no patient ground connected. It's still laying there on the table waiting for us to plug it. We'll first fix the cap for a bit. Yeah. We can have the impedance measurement both in a grid layout or in the head layout. You can configure that using the initialization of the impedance plotter. And then you can connect this, and we will see that the impedances are not too bad. Actually, the highest, if I quickly look, is the mastoid on this side. So I'll quickly try and get it a bit better. It's also sitting a little bit loose there, but it's quite okay to get everything below at least 50K. Okay, what we can do then right now is again close this window, and then we'll continue to a sample plotter. In this case, we will see many different channels, and Baran can blink right now for a bit, which you'll definitely see on this screen. Okay, thanks, Baran. Now I will ask Baran to close his eyes and see if we can detect some alpha waves there. I'm not sure. This is also always a little bit curious on whether the subject may do this. I think we can make out a little of it. Okay, there you see how easily we can start an EEG measurement with relative acceptable impedances and signals. And yeah, thanks, Baran. Yep. So with that, I've come to the end of this webinar, and I wanted to thank you all for your attention. And if you have any questions, please shoot.
Thank you, Joost, for your presentation and the lovely demonstration as well in combination with Param, very clear. I didn't receive any questions on the Q&A button, so I don't know if there are people who want to ask their questions directly to Joost. You can use the raise your hand button and I can unmute your microphone, but I don't see anything. No questions so far. I hope everything was clear then. Yeah, you mentioned, oh, sorry. Yeah, oh, there we have one comment, not a question, from Bertolt Stegeman. Thank you. He says, good intro, no questions. So
it's always good to hear, of course.
Yes, definitely. It was also very lovely, also for the EEG measurement. Very fast as well. Well, you said that you can only store your files in poly5 format, right? That's correct, if I understood correctly. Okay. So it's not possible to load also different types of files into your Python interface.
Yeah, it would be if there are other libraries available that make that those type of files available to you. But as far as we have found at this moment and support at this moment, it's limited to the poly5 files.
Okay. And are there plans to extend the examples? Because we have now the impedance measurement, the plotter. What are the next plans to extend this?
Something that will right now there are actually two major plans. First of all, we'll see if we can gain any performance on the plotter to make our interface more robust to extreme settings, so to say. We have did some testing, of course, to guarantee that the first release is already good to work with, but there may be some things we have overlooked in the first release, so we may find some performance there. Something else, as I already indicated, is that one of the file formats we're looking into is the extensible data format. And that's also something that we have started working on and something we hope to be able to add in a future release. Of course, we'll also show an example with that if it's implemented. And possibly we could make an example that simultaneously saves the poly5 file and XDF file, or just single save it to a, or exclusively save it to the XDF file. That's something that we'll see and evaluate in the coming weeks or months.
Okay, thank you.
In that, it's also quite interesting to get some feedback on that to know what will be most relevant to us, for us to develop.
Okay, that would be great if people start using the Python interface, what they're missing. So feedback is always welcome. So you're all invited to try it out and give us some feedback. What would you like to see? What would you like to measure? So we can start working on that as well. Yeah. Nobody else has a question. Okay. Yeah, then it's a really short Q&A session. Maybe some more interaction. I also don't know if people already downloaded the interface already, or if they already worked with it and ran into some issues or need some help, or that you just have to start. And
something that I didn't mention yet is how to obtain it, of course. That can be downloaded via the support page by filling out a form, and they will receive a download link to the repository containing our interface.
yes, and it's for free, so everyone can download it. Of course, you will need a Saga to use it. We have one more comment from Bertolt Stegeman. He waited for the intro to try it out. It's on the list for next week. Oh, well, that's great. Thank you. We hope you will be satisfied and you can work with it. And we hope this intro helped as well. So thank you, Bertolt, for all your comments. Thank you. I have, and he says thank you as well to you, Joost. So that's great. I have one more question. If you close the plotter and everything, then it stops measuring. It stops acquiring data. So you always have to keep the plotter running to acquire the data in this example script.
Yeah, that's correct. You would be able to minimize it though, so that it's not in your view. That's not a problem. It would just continue running in the background till your measurements will be ongoing.
Okay.
Also, sometimes starts in the minimized view. So then you have to open it. Then it also works.
So you have to keep an eye out for it. If it doesn't appear, it's probably somewhere minimized.
Yeah.
Okay. We have one question from Donghoon Chun. Do you plan to make code for multi-thread GPU use?
It's not on our list at the moment, but then maybe I'm not sure on how much time that would take us, of course. It may, if it definitely has some benefits fits, then it may definitely be something we'll be looking into. But for now, we don't have plans for that.
Okay, thank you for answering. And Donghoon, thank you also for your question. I hope this answers your question. It might be in the future a development, but for now, not yet. Are there more questions? I also don't have any questions anymore. So if there are no more questions, I think I can bring this webinar to an end. Of course, thank you, Joost, for your time and effort and also for presenting today. Yeah, then you can now start your own measurements with the Python interface and try it out yourself. If you need any help, of course, we are there. So you can always contact support@tmsi.com and we are always happy to help out. Further, I hope you enjoyed this webinar as much as I did. And I hope you enjoyed the Python interface even more. So thank you all for joining. Further, we are working on many new developments and more webinars are coming up. So you're always invited for the webinars and I hope to see you there. So definitely keep an eye out to your mailbox. They will be announced through email and also on our LinkedIn page. So follow us on LinkedIn and you will be notified if we have a new webinar and new news. So have a nice day and well, hope to see you next time. Bye-bye.
Bye-bye all.